Okay, let's do a couple of these. The web work. Okay, ready to start? Okay, are you ready to start? Okay, you ready to start, please? Okay, are you ready to start, please? Okay, are you ready to start, please? Okay, are you ready to start, please? Okay, so let's do this one from the web work. Are you ready to start, please? Are you ready to start, please? See, you think it's okay if you do it, but then if 20 people do it, then this loud, so everyone needs to stop talking. Okay, so we're going to work on this one. And why do we need implicit differentiation? Because we can't write y as a function of x. They're two tangled up together, right? You've got a 2y squared, and then we have an e to the y. It would be very difficult to write as y as a function of x, if at all. Okay? But then we kind of pretend that that's true, and so we imagine that this exists. Okay? But this does exist, although this doesn't. Okay? But we pretend that it does. Okay? So if y is a function of x, then how do we take the rate of change of e to the y? So we're going to take the rate of change per term. So we're going to have e to the y. But y is a function of x. So by the chain rule, this is like a composite function, right? So times. And then rate of change of 14, 0. Rate of change of e squared, 0. And then we got 12x, rate of change, plus, remember, so 2, so what's the rate of change of 2y squared? 4y times, by the chain rule, we need y prime. This is a composite function. Y, we're considering y as a function of x. Okay? All right, so what do we do? Every term that has a y prime goes to the left. Every term that doesn't have a y prime goes to the right. So we'll have e to the y prime, minus 4y, y prime, equals 12x. That allows us to factor out y prime, because that's what we're interested in. So once you've moved every term with a y prime over to the left, then you can factor out y prime. And then solve for, and that is our, what is that? That's the rate of change of this with respect to both x and y. So it's with respect to any ordered pair on the graph. Any ordered pair on the graph, this equation will give the rate of change. So they want it at 1, 2. So x equals 1. So we get 12. And here's, so this is a nice thing about web work. A couple things I'm going to show you. First thing is you can enter expressions in. So you see this answer box and you immediately think, oh, I got to get my calculator and get a decimal. Okay, you don't. You don't. You can let web work be the calculator for you. That way you never have to try to figure out how many decimal places they're looking for. Or you never have to make a mistake computing. And then there's one more thing about this I want to show you. So we got 12 times 1 over e to the, what is y? 2 minus 4 times 2. Now here's another thing. So I'm giving you guys limited attempts on these web work problems, limited attempts. So what you can do is, before you use an attempt, you can preview and get to see exactly a nicer image of what you've put in. So if I go to preview here, it shows me, it says right here, answer preview. It says, hey, look, this is what you put in the answer box. It's a nice, especially this is very helpful when it gets complicated with like x and y's and things. Okay, but this is what we wanted, 12 times 1 over e squared minus 4 times 2. That's what we wanted, okay? So I didn't use an attempt there, but I get to see the way that web work interpreted what I wrote in here, so I might have to adjust my parentheses, but I can do that without wasting an attempt. So that's another advantage to putting in an expression is you've got this nice answer preview feature that does not waste one of your attempts. And now I'm ready to check it. Got it. Okay, questions on this example? So use WebWork to put in expressions for your answers. It's really helpful. And then use the preview button. Questions on this one? Let's do one more. I guess number 4. This one. Okay, let's do this one. So we're gonna find dy dx. We're gonna go one term at a time and just follow all the rules that we learned for the mastery, and then remember that whenever you have a y, chain rule will apply because y is a function of x. So whenever you have a y, you're gonna have to apply the chain rule. Okay, so here we go. This one, rate of change of what's the overall structure of the left? Square root. So we're gonna do 1 over 2 square root. And then times the rate of change of the inside, right? 1 plus y prime, or 1y prime, yep. Okay, so that's the rate of change on the left. And then on the right, rate of change of 9 is 0, x squared, y squared. Product rule. Whenever you have a product of functions, you must use the product rule in all circumstances. So we do the first times the derivative of the second. Derivative of the second is 2y. Chain rule, y prime, plus the second times the derivative of the first, y squared times 2x. Questions so far? So how many total terms do I have in this, on both, totaling up all the terms on both sides? How many terms do I have? Notice this is 1 plus, right, in here? This is 1 plus. So I'm going to distribute this to both of these. And so I have a total of how many terms? 4 total terms. Okay? 2 of them have y prime. 2 of them don't. So the first one that has a y prime is when I multiply this times the y prime. So when you have y prime times 1 over 2. Okay? Plus 1 over 2 radical x plus y. And then I'm going to move, let's go ahead and move this over. Anyway, so that's what the left-hand side is when I multiply it out. So now I'm going to move. So it equals this. Okay, and so then this needs to go to the left. This needs to go to the right. So this is going on this side. This one's going to go this way. So we're going to get minus 2x squared y prime, equals 2y squared x minus 1 over 2 radical x plus y. Okay, then I'm going to factor out my y prime, which is essentially dy dx. And I'm going to have this, right, divided by what's left when I factor that out. This would be the 2y squared x minus 1 over 2 radical x plus y, all over this minus this. Is that still on the screen? Here's a good, will be a good one to use the preview answer. So let's write this in and see how the preview answer helps us. And if you want to use the negative exponents, like negative 1/2, that's fine. So here we go, 2y squared x minus 1 divided by, parentheses, 2 square root x plus y. 2, 3. Okay, that's the numerator. Divided by 1 divided by 2 square root x plus y minus 2x squared y on parentheses. So, really tough to know if I've got my parentheses right. Okay, I'm trying to recreate this in a linear left to right format using the right parentheses, so I can check it with the preview answer. Really helpful. And that's what it's showing me. Does that match up with what I wanted? 2y squared x minus 1 over 2 radical x plus y, 1 over 2 radical x minus 2x squared y. I think it's the same. Got to see that it was indeed what I intended without wasting an attempt. Check answer. Okay. Any questions on this solution or web work for this problem? Last chance. We're going to move on. Okay, so we'll do a top hat at the end today based on what we do in class. Okay, so I got this ladder. It's up against the wall, and I've got this very tricky monkey, and he kicks the bottom of the ladder, and it makes the ladder fall. Okay, so here's the setup. A monkey kicks a 10-foot ladder that's flat against the wall so that it falls as shown. How fast is y, the distance from the top of the floor, changing with respect to x, the distance to the wall? Is the setup make sense? Does it make sense? So basically what we've got here is we want to start by defining our quantities here. X is the distance of the bottom from the bottom of the ladder from the wall. That's x. And y is the distance from the ground up to the top of the ladder. And the ladder is 10 feet. Okay, so in these, when you've got these application problems, you always want to draw pictures and define your variables specifically. Okay? Define them specifically. So here's the setup. So the quantity being asked for, how fast is y, the distance from the top of the floor, changing with respect to x, the distance to the wall? What are we asking for there? How can we represent that symbolically or mathematically? What is being asked for here? The rate, how fast y is changing with respect to x. What is that? You should all know what that is. Yeah. dy over dx. dy over dx. Yeah, that's the rate of change. That's the rate of change of y with respect to x, or we know we also use y prime for that. Okay, so now you've done a lot of problems where you were finding y prime or dy dx. What are you going to need to figure out what dy dx is from the start? What are you going to have to know what y prime or dy dx is? Okay. Accumulation. Okay, so it's not necessarily accumulation now. More generally.
You need some sort of function that, or not function, but something that relates x and y equals.
Okay.
I was just wondering if you recorded.
Yeah. Thanks. Yeah. No, not 2 points. No, so what he said was exactly right. Okay, we need an equation that relates x and y. So you just took it for granted because every problem that you did for today's homework, that's what you started with. But so it was you kind of fall into a trance. You don't even realize what's happening, right? So because it's just. But now that you come to these problems where it's an application problem, you're not going to be given that. You're going to have to come up with that. You need an equation that relates x and y. according to the situation. But now that you've heard that, do you realize that every problem that you did for homework today started this way? They gave you an equation of x and y, right? We just took it for granted. We didn't really identify that. But so now we have to, because now we're going to have to come up with that equation of x and y. So do we have a relationship that holds true as x and y vary? So as x and y vary, we need an equation that relates the value of x and y that holds true as x and y vary together. He wants x squared plus y squared equals 10 squared. Is it true? Is it always true? Is it a 90-degree angle? Yeah, so we'll assume that this is a normal wall in a normal room or whatever. Yeah. Okay, yeah, so no matter at what point the ladder is falling, we always have a right triangle with legs x and y. And the hypotenuse is 10. So x squared plus y squared equals 10 squared. And that remains true as x and y change together. That remains true as x and y change together. So it's a relationship that we can start with. So now we want to figure out what dy dx is, or y prime. And you should be experts. Go. You got 1 minute. What is dy dx? You have 1 minute. Don't start by solving for y. Do not start by solving for y. Use something new that you've learned. Everyone get it? What do you do first? Take the derivatives of each, right? Each one with respect to x, right? With respect to x, so we get on the right side, derivative is 0. On the left side, we get 2x plus 2y prime equals 0. That's what you should have gotten. Solving for y prime, you should have got negative x over y. Did you get that? You should have gotten negative x over y when you solve. Review, right? So that's review. But now we have a meaning for this, right? In this particular context, y prime, what does it mean in this particular context? Yeah. Okay, in this context, what does it mean? Yeah. How fast the ladder is falling, right? Because it's dy, right? So how fast the top of the ladder is falling. Okay, but there's more to it. Rate of change always deals with two quantities changing together. You can't have rate of change without two quantities changing together. Yeah. Yeah, so how fast y is changing, right, for a change in x, or with respect to x changing. Okay, so this is exactly what was being asked for here. How fast the distance from the top to the floor is changing with respect to the distance of the bottom of the ladder to the wall. Okay, so how fast is the top of the ladder falling when it's 8 feet above the ground, 5 feet above the ground? Go. So work together. How fast is the top of the ladder falling when it's 8 feet above the ground and 3.5 feet above the ground? Go. Work together if you need help. Okay, so what do we need to figure out that rate of change, dy dx? We found an equation here, negative x over y. So how can we get that? How can we get dy dx? So we've got y is 8, so this equals what the heck is x? How are we going to get x? Yeah. Right, so that we have that, remember, that was our original equation that related x and y. So if y is known, then so is x, according to that original equation. What'd you get? For x, 6. Positive 6. Right? Therefore, dy over dx is negative 3/4, or 0.75. What per what? What per what? What's their units on that? Feet per second. Is it feet per second? What is it, Joseph? What's that? It definitely has units. Feet squared. Not feet per second. We have not talked about time at all here. So time is not involved here. Time is not involved. It's strictly how fast y is changing with respect to x. How x is changing. Feet per, someone said it. Feet per feet. Feet vertical change per foot horizontal change. Those don't cancel out because they're not the same, right? Feet. So this what was the saying? The saying that the ladder is falling. All right, so here we go. So we've been working on all semester. Who can interpret then this negative 0.75 feet per feet? We've worked hard on this. This is a rate of change. Who can explain negative 0.75 feet per feet? If what? Then what? Yeah.
If the vertical height of the ladder, there's a small change in the vertical height of the ladder, the horizontal change will be 0.75.
That's dx dy. That's dx dy.
Oh, flip it around.
Okay.
So for every small change in horizontal
Okay.
feet, the vertical change is going to be 0.75 times that.
That's right. So there's another hand back here. Yeah, so given a small change in what, x? Given a small increase in the bottom of the ladder, what? The top of the ladder is going to go down 3/4 as much as that small change in x. dy equals k dx, or m dx. So when the ladder is here, when x is 6 and y is 8, for a small change in x, what? The top of the ladder goes down 3/4 as much as whatever your change in x was. Right? That's our meaning for rate of change. dy equals m dx. Okay, and what'd you get for when it was 3.5? What is x? Say it again? 9.37. Someone else get that? And the rate of change? Negative 1.2.6 something. 2.68? So what now so much, so I'm showing the first situation, right? Now if I show the second situation, yeah, thank you. Feet per feet, good, okay, and so then, $3.5, so x is 3.5, somewhere around here. Now what's happening here compared to what's happening before? So if it's negative 2.68 feet per feet, what can you say about how the ladder is falling? Somebody knew? if yeah. That's right. Good. So it's going to fall right now. So now later on here, when we got these x values, x and y values, for a small change in x, what y is going to fall like more than 2.5 times as far as whatever change in x you have. So so as and you can see it as the ladder falls. It's not what I wanted. Okay, so now so as the ladder falls, you see that for changes in x now, there's not much of a change, but then at the end, for a change in x, you have a much greater decrease in y for the same change in x. And you can see that dynamically. Okay, questions on that? So that's a lot of review right there. So now we're taking this implicit differentiation and putting it into a real world situation, interpreting the results. Okay? So let's take this a step further. So now what if so we did all that, right? So we said the expression gives the rate of change of y with respect to x, or how fast the top falls relative to the bottom moving in feet per feet. Okay? In feet per feet. So now, the question that we want to ask is, how fast is the top of the ladder falling in feet per second? How fast is it falling in feet per second? So we're bringing a new quantity into this now. What new quantity we're bringing into this? Time, okay? And so we're going to say the time in seconds since the monkey kicked the ladder. We're going to have a new quantity, the time in seconds elapsed since the monkey kicked the ladder. All right? And so we're going to suppose that the bottom is sliding out at a constant speed of v, okay? V feet per second is how fast x is changing, right? So we could say that the distance x is v times t. So then what is dx dt? What's the value of dx dt? It's a nice easy derivative. What is dx dt equal to? V, right? It's v. It's right? This is like x equals 3t. X equals 3t, so what would dx dt be? It'd be 3. In this case, it'd be v, okay? So dx dt is v, and that makes sense, right? Dx dt is the rate of change of x with respect to time. And we said that's that constant speed of v feet per second. Okay, so now we can start back with our original equation, but now, what? X is a function of t, and y is a function of t. Those are both changing with respect to t. So we're going to take the derivative again, but now instead of with respect to x, with respect to t. So when I come to 2x, we need chain rule everywhere now. So x is a function of t, so it's some function of t squared. That's chain rule. And then y is a function of t, and so you have some function of t squared, chain rule. So for now, when we bring time into it, we have chain rule for every quantity. So it's going to be 2x, then by the chain rule, times dx dt, plus 2y, then chain rule dy dt. Make sense? Okay, so when I solve that, if I solve that for dy dt, that's what we were interested in. How fast is the top of the ladder falling in feet per second? Then I'm solving for dy dt. And if you get negative x over y dx dt. And what was dx dt? V. Okay? So this is called a related rates equation. Okay? Related rates. Why? It's an equation that relates two or more rates. We've never seen this before. We've always just focused on one rate of change at any given time. Well, now we have two rates of change, and this equation tells us how those are related. As x and y change together, this is how the rate of change of y with respect to t and the rate of change of x with respect to t change together. Okay? So, a related rates equation is an equation that relates two or more rates of change. So, where does it come from? What was the source of the related rates equation? What's the source of the related rates equation? Nope. Nope. Where did this particular related rates equation come from? How did we get it? From what? X squared plus y squared equals 100. Okay? So the source of the related rates equation is the equation that related the associated quantities that we started with. So we had an equation that related the quantities x and y. By taking the derivative implicitly, we can get the equation that relates the rates, dy dt and dx dt. Okay, so this is the whole ball of wax here for these. To get the related rates equation, which is the most important thing, that's what this solution will revolve around. The related rates equation, the equation that relates two or more rates. That's the prime focus of the solution to your problem, the related rates equation. Where does it come from? So it's first you must have an equation that. You first must have an equation that relates the quantities for those rates. That's where that related rates equation is going to come from. All right? So here's what we're after. This is the centerpiece of the solution. It's the focal point. Where does it come from? It comes from the equation that relates the associated quantities to the rates that we're relating. That's a big takeaway. Because these are all different. All these problems are a different context. But this is what stays the same. We're after an equation that brings together two or more rates of change. And we're going to get that by differentiating, taking the derivative of the equation that relates those quantities to start with. So let's practice. Let's give it a shot here. So the edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? So we have a growing cube, right? For whatever reason, it's growing. How fast is the volume changing when the length of each edge is 50 centimeters? What is our goal for this solution? What is our prime focus for the solution? Related rates equation, an equation that brings together rates that are related, okay? And where's that going to come from? Where's the related rates equation going to come from? The quantities equation, the equation that brings the quantities together. This is going to be the structure of every solution to this kind of problem. Okay? You need some consistency. Why? Because the contexts are all different. You know, when you on the exam, you're going to see a context that's different than anyone you've seen before. So you need an anchor to hold on to. Okay? So here's the approach. First, identify all the rates that are mentioned in the problem. So, what's one rate mentioned in this problem? 2 centimeters per second. Okay, and that's the rate of change of what? Of edges growing, right? What other rates are mentioned? The rate of change of the volume. It says how fast is the volume changing? So those are your two rates in this case. How fast the edge length is changing, how fast the volume is changing. So eventually we're after this equation that's going to bring those rates together. Okay? So, but first we're going to need the quantities equation. So what quantities, this is the easiest step. So what quantities are associated with each of these rates? First rate, quantity is edge length. Second rate, quantity is volume. So let's define those, right? So let's let S be the edge length of the cube and V be the volume of the cube. So if we're after the related rates equation, what do we need? The quantities equation. We've got quantities S and V, and we've got a cube. So what is the equation that relates these quantities, S and V? It's a cube, right? So it's going to be S cubed. So I'm using function notation here. That's not V times S, that's V of S. So that's a function. V of S equals S cubed. That brings together volume and side length. If you cube the side length, you get the volume. And now that we've got the quantities equation, we can write, this is our whole goal. The whole goal is to get the related rates equation. Okay? What is the related rate? How do we get the related rates equation from the quantities equation? How are we going to get rates of change out of this? How are we going to get the rate of change of volume and the rate of change of side length? Take the derivative, right? So we're going to take the derivative, but now remember, it's going to be with respect to t. So everything's going to involve chain rule. We're going to need chain rule everywhere. So we want the rate of change of v with respect to t on the left. And on the right, we want the rate of change of s cubed with respect to t. So both the left side and the right side with respect to t. So the left side becomes rate of change of volume. Well, you could say that's just like 1, right? 1, but then by the chain rule, dv dt. And then what about the right side? Rate of change of s cubed with respect to t. What will it be? 3s squared times ds dt. Yeah, times ds dt. Okay, so there is actually taking the derivatives of both sides. Chain rule for both quantities. Chain rule for both quantities. Okay, and then the last step now, so this is, we've kind of arrived at, this was our goal, right? The related rates equation. The equation that shows us how the volume rate and the side length rate are always in relationship together. So now we're just ready to solve for what we're asked for. What are we asked to solve for? How fast is the volume changing? Which one is that? dv dt. So if we're going to find dv dt, that means we need to know we should be able to figure out everything else. That means we should know or be able to figure out s, and we should know or be able to figure out ds dt. Do we know s? What is it? 50. We want that moment that it's 50. And do we know ds dt? Yeah, that's how fast the edge length is changing. That's 2. So we got everything we need. We're home free. So dv dt is 3 times 50 squared times 2, which is 15,000 centimeter cubed per second. That's how fast the volume is changing per second at that moment around when the edge is 50 centimeters. Questions on the example? Okay, remember? This is our goal and the focal point of the problem. Where does it come from? The equation of the quantities, right? So again, this goes back to this. Our goal is this equation that relates the rates. That's going to come from the equation that relates the corresponding quantities. You guys try. Move fast, move fast. So what's your thought process about the solution? It should be this. Your thought process should be this. We're after a related rates equation that is going to come from a quantities equation. So, here's the approach. Identify all the rates involved. Identify the corresponding quantities. Write the equation that relates those quantities from which you can get the related rates equation. Solve for the unknown rate. Go. You're either making progress or you're getting help. Those are your choices.
power flows. Three over here. Those cancel out.
So what rates will we have? Okay, so symbolically, dr dt and dv dt. The rate of change of the radius and the rate of change of the volume. How fast the radius is increasing, how fast the volume is increasing, and we can write those as dr dt and dv dt. Okay? Therefore, our quantities are v and r. What's the equation that relates v and r? It's the volume of a sphere. Make sense? And so what are we after? We're after the equation that brings together dv dt and dr dt. How do we get it? Implicit derivative, right? Implicit derivative. Derivative of every term with respect to time. So, derivative of v is derivative of the right. What happened to the 4/3 pi?
4 pi r squared.
Yeah, so 3 times this will be 4 pi r squared dr dt, chain rule, chain rule. What's our unknown? What are we trying to find? This is the unknown now. That means we have to know or be able to figure out every other thing. We have to know or be able to figure out every other thing because that's what's unknown. So do we have dv dt? What is it? 150. Do we have r? Okay. Are we able to figure it out? From how? Yeah, so the volume is 500, so we can come to our equation and get the corresponding r when the volume is 500. take that r and put it into our related rates equation. Anybody have that? 923. Someone else got that? Agree? Cool. So where does that radius come from? It comes from this information about the volume that now we can get that radius for the given volume. You find the radius from here, get the value of r, and that's 4 pi r squared. So squared. Sorry, this is squared. Is that better? Yeah.